Imagine standing at the edge of everything you know, looking into a region where the rules that shaped your entire understanding of reality no longer apply. A place where time stretches, space bends, and cause and effect lose their familiar meaning. This is not science fiction. This is what modern physics predicts happens near a black hole, an object so extreme that it exposes the fault lines in our deepest theories. Black holes are not merely cosmic curiosities. They are laboratories where the universe reveals its hidden structure by breaking our expectations. To understand why they are so important, we need to begin with how reality itself is supposed to work. According to Einstein's general relativity, gravity is not a force in the usual sense. It is geometry. Mass and energy tell spacetime how to curve, and curved spacetime tells matter how to move. This elegant idea explains the motion of planets, the bending of light, and the expansion of the universe with extraordinary accuracy. When enough mass collapses into a small enough region, space-time curves so severely that it creates an event horizon, a boundary beyond which all paths lead inward. From that point on, the future points only deeper inside. Nothing that crosses this boundary can ever influence the outside universe again. For a long time, physicists believed this meant absolute loss. Whatever fell into a black hole was erased from reality, except for a few basic properties like mass, charge, and spin. Everything else was gone. Then quantum mechanics entered the picture. Quantum theory describes nature at its smallest scales, where particles behave like probabilities and information plays a central role. One of its most fundamental principles is unitarity, the idea that information is conserved. The universe evolves in a way that never truly destroys information. Even if systems become chaotic or scrambled beyond recognition, the underlying data still exists. This principle has been tested endlessly and has never failed. When Stephen Hawking combined quantum mechanics with curved spacetime, he discovered that black holes must emit radiation. This radiation arises from quantum fluctuations near the event horizon and slowly carries energy away. Over vast timescales, black holes shrink and eventually disappear entirely. What remains is a cloud of thermal radiation with no obvious memory of what created it. This is where the conflict becomes unavoidable. If the black hole evaporates completely and only random radiation remains, then the information about everything that ever fell in seems to be gone. But quantum mechanics forbids this. The paradox is not about ignorance or missing data, it is about logical inconsistency. Two pillars of modern physics make mutually exclusive claims. Either black holes destroy information, or our understanding of spacetime is wrong at a fundamental level. To make matters worse, relativity tells us that nothing special happens at the event horizon for someone falling in. There's no physical surface, no dramatic signal, no sudden explosion of energy. Crossing the horizon should feel no different from floating through empty space. This creates a nightmare scenario. From the outside, information appears to be stored at the horizon and released slowly through radiation. From the inside, the same information falls through and continues inward. The same information seems to exist in two places at once. In quantum mechanics, this is forbidden. This duplication is known as quantum cloning, and it cannot happen. Something has to give. To resolve this, physicists began rethinking what information actually is and where it can live. Jacob Bekenstein proposed that the entropy of a black hole is proportional to the area of its event horizon, not its volume. This suggested that information is encoded on surfaces, not in regions of space. This idea grew into the holographic principle, the claim that all the information contained in a volume of space can be represented on its boundary. According to this view, the three-dimensional world we experience may emerge from more fundamental two-dimensional data. Black holes are not empty containers, but dense repositories of information written on their horizons. Yet this only deepens the mystery. If the horizon stores information, then it must have physical structure. It must be able to interact, record, and process data. But relativity insists that the horizon is locally indistinguishable from empty space. These two descriptions cannot both be true in the same way. The tension between them suggests that space-time itself may not be fundamental. It may be an emergent phenomenon arising from quantum information. In this picture, geometry is not primary, relationships are. Entanglement, the strange quantum connection between particles, may be the true scaffolding of reality. Regions of space are connected because their quantum states are correlated. Distance is not fundamental, connectivity is. Black holes, with their extreme entanglement structure, push this idea to its limit. They may represent regions where space-time dissolves into pure information, where classical geometry fails and a deeper description takes over. As physicists explored these ideas further, the paradox grew sharper rather than softer. If information escapes in Hawking radiation, then that radiation must be entangled with whatever remains inside the black hole. But quantum entanglement obeys strict rules. A system cannot be fully entangled with two independent systems at once. This leads to a contradiction between the smoothness of space-time at the horizon and the requirements of quantum information. To resolve this, some researchers propose the existence of a firewall, a region of extremely high energy at the event horizon that would destroy any infalling observer. This would prevent information duplication, but at an enormous cost. It would violate the equivalence principle, one of the cornerstones of general relativity. It would mean that space-time itself becomes violently unstable at the horizon. Others argued that the paradox reveals a limitation in how we think about observation. According to black hole complementarity, no single observer can witness both the interior and exterior descriptions of a black hole. The apparent duplication of information never leads to an observable contradiction because the information cannot be compared. Reality depends on perspective, and demanding a global description may be a category error. This idea preserves both quantum mechanics and relativity, but it leaves a lingering sense of incompleteness. Then came a more radical proposal. The connection between entanglement and geometry suggested that space-time might be woven from quantum correlations. In this framework, the interior of a black hole and the outgoing radiation are not separate systems. They are parts of a single, highly entangled structure. Some physicists summarize this idea with the phrase, "entanglement is space-time." In this view, information does not need to escape in the classical sense. It is never truly separated. The interior and exterior remain connected through quantum geometry, possibly resembling microscopic wormholes. Information is preserved not by traveling through space, but by remaining encoded in correlations. Even Hawking eventually revised his stance. He suggested that true event horizons may never form in a strict sense. Instead, black holes might have apparent horizons that trap matter temporarily, but eventually allow information to leak out. Quantum fluctuations could prevent the formation of a permanently sealed region. If this is correct, then the paradox dissolves because one of its assumptions is false. There is no eternal prison from which information cannot escape. These ideas have consequences far beyond black holes. If space-time is emergent, then time itself may not be fundamental. The flow of time we experience could arise from the growth of entanglement or the processing of information. The universe may not evolve in time. Time may emerge from the way information is organized. Black holes then become windows into the underlying code of reality. They are places where the illusion of classical space-time breaks down, revealing the quantum structure beneath. Even the universe as a whole may be holographic. The observable cosmos has a horizon beyond which information cannot reach us. The total information content of our universe may be encoded on a distant boundary, with space and matter emerging as projections. This is not mystical speculation. It is a serious consequence of combining gravity, quantum mechanics, and thermodynamics. Black holes force us to confront these ideas because they sit at the intersection of all three. They are not merely objects in space, they are stress tests for reality itself. Every paradox they generate is a signal that our current concepts are incomplete. The fact that information seems threatened tells us that information is fundamental. The universe does not forget. It transforms, it encodes, it hides, but it does not erase. Black holes, once thought to be cosmic graves, may instead be archives. Not libraries in the classical sense, but dense knots of quantum relationships where reality is compressed to its limits. Understanding them may require abandoning our intuitive notions of space, time, and causality. But in doing so, we move closer to a deeper truth. The universe is not built from particles alone. It is built from information and the laws that govern how that information can be arranged. Black holes are not the end of physics. They are the beginning of a more complete picture, one where reality is richer, stranger, and more interconnected than we ever imagined.